Welcome back, my friends, to the unofficial Mac platform layer for Handmade Hero. We are making a video game 100% from scratch. I would usually say no libraries, but it's more like some libraries, some leaning on other people, but really trying to minimize that. You could call this minimalist programming. You could say it's maybe even starting with some libraries, but just gradually reducing that reliance and becoming more self-reliant so that you can make whatever it is that you want to make without being beholden to someone else's thinking, without inheriting a large pyramid of crap that you don't want, and being able to be as nimble and as efficient as possible. So with that said, yesterday we wrapped up debug file IO, and there are a few things we probably still want to clean up, but we're not really going to get to that. So I actually just noticed this like right here. I'm going to put a little to do here. So just move this to the header file, right? So that's a to do, and move this as well. These are things that are like, if you were really pedantic about programming and, always had to have things a certain way, you might flip out that these are not in the header. But I am not pedantic about programming, and I don't think you should be either, although that statement itself could be construed as dogmatic. But either way, I don't really care that this, is here. We will move it because we like to be clean sometimes, and we like to have our structs kind of out of the way and, blah, blah, blah. So we'll do that when we want to, but we're not doing that today because today we are focused on video sync. And what do we mean by that? So this is something I've kind of briefly gone over. I guess there was one day where we were talking about refreshing the display or something, or like what a game engine looks like. And I actually had gone over it when answering a question, why does the CPU spin up to like 100% when this thing is running? And the reason is because we haven't, what I said is we haven't really enforced a video frame rate yet. And I maintain that reasoning. So typically what goes on in a lot of games, and really the way that you want to think about games, I'm opening some stuff here. So I'm going to open up Sketch. This is something I've kind of gone over a bit. So let's see. We got 3 boxes here in a game. All right. We've got, okay, so games pretty much need to do these 3 things. They need to gather input, right? And then they need to update the state of this stuff that you're simulating something in a game. You're simulating some kind of world. We call them entities. That's probably the best word that we have for it now. It's stuff that exists in the world. Whatever state, you could call this updating the state of the game, right? So things. So we get some input from a controller of some kind, a game controller, keyboard, whatever. And we take that input, and then there's stuff that we want to that we're simulating where we update its state. So things like, I don't know, if we're playing Super Mario Brothers, then you're going to update Mario's velocity and position, and maybe update the position and velocity of the Goombas, and maybe accelerate them, and maybe there's a camera position and you want to move the camera some other place so that you can, given all this information, do the final step. Oh wait, I want text, which is to render. Okay, so we input, update, and render, and we go in this order always. And the important thing to note, this is a terrible drawing, is that this actually occurs in this order on every frame. So every time you go through and make a frame, this is what you're doing. Getting input from a controller, updating the state of the world, and then rendering the result of that world state, as a picture or some sound. Now, it is actually pretty darn important that this thing happen at a certain kind of a frequency. So it's really important that it happen at some multiple of 30 frames per second. So that could be 60 frames per second. It could be 90, 120. And the reason that we pick 30 is because that's the typical kind of, that 30 or 60 or 120 or 90, there's some multiple of the monitor's refresh rate. So you can't actually see it because your eyes are it's just sort of the result of biological evolution. Your eyes are able to kind of create this sort of subjective picture of what reality is like. When looking at your monitor, what's actually going on is like 60 frames a second. This thing is like scanning across the top and like, drawing some stuff, right? And actually it used to be the case with like the old cathode ray tubes that it was like a light beam like shining, right? And like scanning, so that was actually happening. But modern displays are a little bit different from that. I'm not obviously not like a display expert kind of person, but the idea is that the video, your display has kind of a frequency to it. It kind of does things like in lockstep. It kind of every 1/60th of a second, it's going to take whatever state is on the computer and it's going to draw a new picture, right? So right now, if we were to run this game and we were to say, which I think we'll do. So let's, I'm in my day 20 directory. I'm just going to build. Maybe there's a few things. Okay. Yeah, so I'm missing this. I'm actually going to move. I'm sorry. I need to like move my test background in there. So I'm going to do that. Let's see. Let's move the test background into. The problem is I'm doing this on GitHub. And then what I'm trying to do is I'm trying to make sure that I'm not like, posting anything that we would consider to be, copyrighted stuff. So I have to keep moving the resources back in. So there's that, and then so go back up, and then rebuild. All right. Okay, so at least we got that. And these warnings, we're gonna go over warnings later. So no need to worry about that. And this is something that you will have seen from one of the previous videos that I've done. What you'll see is we are already calculating frame rate, right? So we're already calculating it, and we already have a way to display that to the screen, right? So or to the console's kind of logging system. So I got this, right? Take this, da da da. All right, so we've already got a way to kind of display that information, right? So I'm going to run this thing, all right, and that's going to show us. Da da da. All right. So you see, we've got this frames per second, right? And it's like all over the frickin' map, right? So we're like 75, 74, 77, 63, 47, like we just, like it's sort of crazy town over there. We're not really, and now this actually becomes kind of a problem. So you imagine what the monitor is doing is like every 60th of a second, it's like, hey, I'm gonna draw a picture, gonna draw a picture, gonna draw a picture, gonna draw a picture, right? And and now like the actual state of like what to draw is being updated at like all these different frequencies. And so maybe like in between when the monitor decides, oh, I'm gonna draw a picture, okay, 1/60th of a second just passed. But maybe in that 1/60th of a second, this thing right here like drew 2 frames, right? And so now like we effectively missed a frame because we didn't draw the one frame that was being drawn that was output to the display buffer, right? We like just straight up didn't draw that one because we kind of like missed our timing, right? We missed the timing with the monitor. And so what we're really trying to do here is we're trying to clean this up. We're trying to make it so that when you so that this is kind of occurring on sync, or at least some kind of sync, some kind of regular sort of refresh rate, so that the video display and the game itself are refreshing kind of at a similar kind of sync. What we're doing right now is going to be more of like a debug kind of a sync. It's not really going to be kind of a super official version, because I do think that there is like a better way to get VSync on a Mac. But this will kind of I think there's like actual ways, like basically when we talk to the GPU in Metal later on, which I think I'm going to do because it seems like people want that. I believe that there's going to be ways to tell it, hey, Metal, what I want you to do is I want you to wait until, because think about this, like it's scanning, right? It's scanning, and then it's like drawing some stuff, all right? But then there's going to be some time like when it's done. And kind of like one way that that's referred to is like, it's called V blank. So one thing we could tell Metal later on is like, hey, Metal, like wait till we hit, V blank. Wait till we hit this point where like you're not currently refreshing the screen, and then let's swap out the buffer. So the buffer swap, so the swap doesn't happen like while you're drawing stuff to the screen, or Casey calls it the flip. But basically what it is it's like we're taking the buffer that the screen is drawing, and we're replacing it with something else. We're replacing it with the next frame, right? And so we don't want that to happen while it's drawing the frame, or like while it's putting the frame to the screen. So these are like kind of important considerations. But this, having said that, we'll kind of get to that later. For now, we just want to get some kind of frame rate in place. Like just like our goal is just to like clean up this mess a little bit, right? So we get to like say, and we're not even going to pick a particularly ambitious frame rate. We're just going to pick like 30 frames a second. And the reason we're picking 30 frames a second is because we can reasonably hit that frame rate. The thing is, right now, our rendering is super freaking inefficient. So if we look at our rendering in this thing, like what are we doing to render? Well, we're not even using the GPU. So I think the thing I call is like Mac redraw buffer or whatever. This is like really flipping, like this isn't how you do it. And I realized that, and basically what I was doing was just getting something going so that you could follow the series, right? Because actually much of the series to start off with, Casey uses a software renderer. And the reason he does that is to kind of like walk you through what a renderer does and like how it works. So that once you do finally move to GPU rendering, you'll be able to understand what the principles are. And once you understand what those principles are, then you can fully take advantage of the hardware acceleration that we have. So the idea is to like really build an understanding, and that's why we start with a software renderer. The problem with a software renderer is it is just not very fast. And that means that it's going to be way harder for us to hit these kind of higher frame rates, like 60 frames a second, 90 frames a second, etc., whatever it is. I don't even know if you can really hit 90 on this. But, all that I'm saying is that's the reason that we're kind of lowering the bar for the frame rate, at least for this rather early kind of platform later. So I will say that much. And so we are going to now get started with this. So we want to go back to our main function, right? And now we're actually talking about setting up a frame rate, right? And so much of this, I think it would probably be best if we did this like right before setting up the time, the frame counter, that kind of thing. So first thing we have is like, we got an integer that represents the monitor refresh rate, right? So monitor refresh hertz. And we're going to say, we're not, again, like I didn't really check what the actual monitor refresh rate is. I don't really want to spend too much time like going into the actual APIs for how you would figure this out on a Mac, but I think it's pretty reasonable to just say for now, and we can even put a to do in here, like, determine this programmatically, right? Because there's probably a way to like figure that out, programmatically what the monitor's refresh rate is. But for now, this is okay. We're going to say it's 60. And then all we're going to do is we're going to say, I don't know, like, actually, I think we want like a reel. So we want this to be in reels. Yeah, so we're gonna say target, frames per second, and that's just going to be the monitor refresh rate, monitor refresh hertz, divided by 2, right? So we're going for 30 frames a second here, right? And then seconds per I think we want seconds per frame. The reason we want seconds per frame is because that value is actually going to be way more useful to us in terms of kind of telling. Basically, what we're going to do is we're going to kind of calculate how much time it took us to update the state of entities in the world, and then and how much time it took us to draw the last frame, and then we're going to see, okay, well, how much time has passed since we did the last frame, and how much work did we do on this frame? And then what we're going to do is we're going to say, well, that amount, like what we want to do is we want to sleep the processor until we hit an amount of time that would get us to our target frame rate, that would get us to 30 frames a second. So we want to sleep the CPU for that time. So we need to figure out how much time did we spend. How much time did we spend actually, like, going through the last frame, and then from there, what's our target frame rate, and then we'll just take that difference and we'll sleep the processor up to a time that is our target seconds per frame, or target frame. That is our target frame rate. Is kind of the thinking here. So let's do target seconds per frame, and that's just 1 over the target frames per second. So we got that, right? So we have a way to, and this is going to be like, you already know what this number is. It's like, seconds per frame is like, it's like 0.3, or it's 0.0333, something like that. Milliseconds per frame is pretty useful too, because that's a little bit more. That's like 33.3 something. Okay, so then we enter our frame loop, right? This is the loop that's just drawing a frame over and over again, right? And now a few things have changed, because now we're kind of starting to get at more clearly defining the different parts of, this is starting to get into the what's going on here. Input, gather input, update the state, render. So what we want to do is like make sure that that all of these things are kind of occurring in that order, right? So that we can kind of properly control the frame timing and video display. And so if I'm looking at this, so far what we've got is, this looks like this first start, this start here, like right here. This is gathering input, that's gathering keyboard input basically, right? So that's good, seems fine. And then this is gathering game controller input, so stuff from like my PlayStation controller. That's great, that's the input, that's what we want to be first, right? Okay. And now this is, this is kind of our sound logic, right? So this is gathering sound, right? So it's taking some of that. What it's doing is it's figuring out figuring out how much sound samples we want to write. So it seems like all the input stuff is up over our game update and render. So far we're pretty good. And we've got game update and render. Okay, so a little hint there. Update, right? So update is now what we're doing is we're taking these inputs and we're updating the state of the world. So we're passing a pointer to the game memory, passing the controller input, the display buffer, and the sound buffer. Okay, so now we've updated, right? And now we've got this render here, because that's what redraw buffer is. It's basically take the buffer that you got from the update thing and then redraw it, like draw it inside. I actually don't really like that name of that function, so I think we're going to change it, because what I think it really should be something like Mac redraw buffer. I think we should have it be something like Mac. It's what it really is it's redraw. It's more like we're it's like we're flipping the screen, or flip buffer doesn't sound right. I don't want to get too hung up on naming. Swap buffer, yeah, I don't know. You could get really hung up on naming. Redraw kind of makes sense, but then I had like a better name too, like not too long ago. It's unfortunate because it's like really was on the top of my head. I don't know. I think, you know what? Now that I think about it, I don't really have a great name. But this kind of represents the render part. This kind of represents the, take the result of the update and then render it. And notice how, and so does this, right? So we've got all this sound stuff here. This is putting the sound into, what this is doing is it's putting the sound into the sound card, right? And so that is just preparing our circular sound buffer. So we're taking the result of the update. So actually this is in order, but I think what we want to do is probably move the draw buffer down after the sound. So right here, actually wait, we probably want to put it like right after we, like the very last thing that we do is we put the buffer to the screen, right? So we flip the buffer. And then this audio stuff, we can think about possibly moving that later. I think once we get, right now for today, we're just looking at video sync. So maybe what we'll do is we'll do a little bit more of like a sound visualizer, or like try and get a little bit more of an accurate picture of what the sound is doing. For now, so far, the sound has felt pretty solid. It's felt pretty responsive. So I'm not too worried about it. On Casey's Win32 platform layer, he had quite a few problems with the sound and spent, probably 2 or 3 days just writing all this visualizer logic for it. I'm not really sure if we're going to do that, because I honestly just don't think that there is much of a problem with ours yet. And another problem too is that just at this early of a stage in a platform layer, we don't really have a renderer yet, and so just having the ability to properly visualize the sound is not really there. So I'm not really sure if we would get very great information out of that. I'm still kind of debating whether we want to do it. Anyway, so we got game update and render, and then then what we're doing right here is this is the end of the frame, right? We could call it end of updates, right? Updates, right? So all the updates have finished. And at this point, I would say this is where we want to start figuring out how much time has passed since the last time we drew a picture and updated the state of the world and all those things. Like, how much time has passed? And so, I'm kind of thinking, what do we call something like that? I don't know. It's like, just call it, you just could call it work counter. I'm not really sure if there's like a great, um, great kind of thing for that. We want to preserve this end of frame time because that's actually, we're going to use this for logging. So we're going to keep this because this is going to tell us, because basically right here is where we're trying to figure out how much time do we want to sleep the processor, right? Like how much time do we want to sleep this thread so that we can hit this timing correctly, right? And so we're going to use this mock absolute time. So, and remember, from the previous one, in order to get kind of any kind of amount of like timing on this, we have to use this absolute time, and then we have to pass this time-based thing. Remember this time-based numerator and denominator? We had set that up, and that's, I think what that is, it just gets like kind of how time works on this machine. And so it's sort of like a unifying, anything that's running this mock operating system will give us one of these time bases, and then we can use that to figure out how much time has passed. And so what we really want is we want something that's like a mac get seconds elapsed, because what we want to do is figure out how much time passed since the last counter, because remember, we're actually keeping track of the end of each frame, right? At the end of each frame. We want to figure out how much time has passed since then and this work counter that we've got. So probably what we want to do is we're obviously going to need to pass a pointer to the time base, right? And then I think what we're going to want to do is pass the start time. So let's see. I actually want to remember what we did here. Mac get seconds elapsed. Okay, so we do pass the last counter, right? So yeah, and the start is, okay, so we passed the last counter. So yeah, the start is going to be, right, the last frame. And then our work counter is going to be kind of like the new time. So we're going to take as the time from the last frame minus the new, or I'm sorry, the time from where we are now, this work counter. This is like this moment in time, right? And then we're going to subtract the time from the last frame. We're going to figure out what the difference is, right? The time difference. And so we just need to define this function first. Right. I'm just plopping this like over our main function because that's really it's where it's being used, and so not thinking too much about where stuff needs to go. What we're doing is we're just kind of getting the foundation in place, or like kind of experimenting here. So this thing is it's real. It returns real. The time is real 32, right? And that will just tell us the number of seconds. So real 32 result. And so what is that result going to be? Well, it's going to be something like we've got this. Let's see. Got the number. We want the end minus the start, right? So we know that, and that's in unsigned integer 64. And so we want to probably cast that to like a real 32, end minus start, right? And then maybe what we want to do is like multiply that times the time base numerator over the time base denominator. Okay. And then I think what we want to do is like to get seconds, I think we have to do 1,000. It's like 1,000 divided by 1,000 divided by 1,000, because it's in like nanoseconds. There's probably a cleaner way to do this now that I'm thinking about it. So, okay. Real 32 n minus star times, yeah. That's probably, let's see what I did over here, elapsed. Oh, okay, so I just took the elapsed, right? I like that. So we do just figure out the elapsed in a separate line. So elapsed is equal to n minus start. Okay. And then what we do is we take this real 32 elapsed times that time-based numerator over time-based denominator, right? And let's see if I, oh yeah, that's right. So elapsed, okay. Yeah, that makes sense. And another thing I forgot too is that this this time base, we're passing it as a pointer, and so that means that when we're referencing its members, we need to do this arrow thing to kind of like dereference them. So that's dereferencing this pointer here. So because we pass as a pointer, so no big deal. Then we can just return this result. So this will get the number of seconds that passed from some start time and end time, right? And that is going to be very useful. So we are going to want to know that. All right, so now we've got some real 32 that's like, how much, you know, I'm not sure what we call that, like seconds elapsed per frame. Or, yeah, we'll just call it work seconds for now. Because it's not really that yet, and I want to do like another, I guess you could say it was. Yeah, I forget. You know what? Let's just say. Well, what we'll do is I don't know. I kind of like making it a little bit more clear. So seconds elapsed for a frame. We're going to start that out as saying that's the number of work seconds, right? So work seconds just meaning like that's as much time so far as the processor has spent working on getting, kind of updating the state of the world and putting the stuff in the buffer, the display buffer, figuring out sound. That's as much work seconds as it's done. Now, the amount of time that is elapsed for the frame right now is this work seconds. It starts off as that, but then that's gonna change, because what we plan to do is right now on most frames this seconds elapsed per frame is actually going to be lower than the target seconds per frame, right? So this is going to be less than that, 0.033 or whatever. And what we want to do, because the way that you hit a frame rate is the work that you do has to be lower than that, right? It has to be less than that. And then what you do is you just kind of, you sleep for the remainder, right? So you sleep up until you hit your framing. You can't do the other way around. You can't be like, well, the amount of time that I spent was more than 30 seconds a frame, or 33.3 milliseconds a frame. And then I well, sorry, too bad, you missed your frame timing. So you have to have a process that's faster than the frame rate that you want to hit, and then you rest the CPU for whatever's left over, right? So I think that's pretty eminently logical. That's math for you. So we got this, and now what we're going to do is we're going to say, okay, well, if the seconds elapsed for my frame are less than the target seconds per frame, then we want to do some stuff, right? And if not, then we've basically got a missed frame rate, right? Because the amount of time that we spent kind of churning through, going through, updating the state of the world, entities, whatnot, gathering input, all those things. That amount, that time, also that includes the amount of time that was spent rendering the previous, putting the previous frame on the screen. So that includes that time. If all of that time is actually more than the amount of target seconds per frame, then just logically that means that we missed our frame rate, we missed our timing. So we obviously would want to do something about that. We would care. And you'll probably see when you miss your frame rate, just in just playing the game. It's going to seem kind of like choppy, but we also, the cool thing about this is, like, logically we know when we missed it, and we can kind of do something about that. So we can log it, we can kind of figure out more of what we want to do there. Okay, so now what we're coming upon is this circumstance here where we need to sleep up to the target frame rate, right? So that's what this condition represents right here. This is like the amount of time that we spend working is less than our target frame rate, and so what we need to do is tell this thread to go to sleep until we hit that target frame rate. And this is sort of the area where it gets a little bit interesting, because if you look at some of these, like, so there is a sleep function. You can go and look it up. It's called uSleep. So uSleep is the function that we're going to use, right? And then that takes like milliseconds, right? So we will use that. But the problem is that you really can't quite tell the processor exactly how long to sleep on most systems. Most kind of consumer grade, like, operating systems just aren't designed for real timing, for you to very precisely tell the processor how long to sleep and how long to wake up. And so there really isn't a very fine-grained way to do that on most kind of consumer-grade operating systems, like your Mac OS, your Windows, that kind of thing. So you would have to have like a custom operating system in order to be able to really very precisely tell it. So what I've discovered, and I'm sure what plenty of other people have discovered as well, it seems like Casey kind of hit upon this sort of thing, is when we use this sleep function, what we're really doing is we're really just kind of guessing. So what we're really saying is try and kind of sleep for this amount of time, right? And then when you wake up, when you wake up after that amount of time, you're probably not going to be at the frame rate. The amount of time that's passed is probably not going to be equal exactly or close enough, or at least like slightly greater than this target seconds per frame. And that's okay, because what we're going to do then is just spin for the remainder. So what we do is we do kind of like a blunt. So this uSleep sort of thing, that's like a blunt force object. That's like sleep for this chunk of time, and it's going to be more or less, mostly what we want. And then when you're done, you're not going to be fully there. So what we're going to do is we're going to spin up until you hit the exact timing, and then we're going to continue, right? And so I don't know if this is going to invite like some rather, if this is going to invite invective or incendiary commentary, because like when I read some of the Apple documentation, like they're pretty darn clear about saying that you shouldn't spin lock. And I get that, like I don't want to spin lock. But maybe they mean that in like a different context. Maybe they mean that like in a less fine-grained kind of context. Maybe like if all we did was we spin locked instead of sleeping, then I think that would be obviously like, pretty awful, because like we're going to generate all this heat and stuff, and like we don't want that. But part of me kind of wonders. So they have these like, a lot of it comes down to like the API that they give you. It's just like they give you this object-oriented API that's like uses this like CAV display link thing, and like that all handles it under the hood. But then I'm kind of wondering, okay, well, if you're doing all this stuff kind of in the background for me, like what are you really doing here? Like I know what this operating system is. Like I know that it's not a real-time operating system, right? So if that's what you're doing, are you doing anything different from what I'm doing? And maybe you are, maybe you aren't, but the problem is I can't actually see what's going on there to know. So that's sort of the weird conundrum or circumstance I'm in. Obviously, I would like to talk to more Apple engineers or more people over there to sort of see what their take is on it. There's almost certainly, given my experience level with this, like there's probably something I'm missing, but with all of that said, here is what we're going to do now. And I am not saying it's the right thing to do. In fact, it could very well be the wrong thing to do. But it's what we're going to do. And so far, it's been okay. So I'll just kind of caveat everything I'm saying with that. What we're going to do is we are going to, I'll just use my code here because why not? I'll just walk through it. We are going to figure out we're going to tell this thing to sleep for some time. That is kind of like the amount of time that where we would hit our frame rate, right? So we would hit our frame rate if we slept. Don't consider this under offset. I'll talk about that in a second. If we were able to very precisely sleep this thread for the target seconds per frame minus the seconds elapsed per frame, if we were able to hit that timing perfectly, then we would have proper video sync, right? You can do the math on that, right? Because we worked this much, we spent this much time already. And so that difference, this is the difference, this is the diff, this is the amount of time we want to sleep to hit our target seconds per frame. This is what's left over, right? So we want to hit that. That's the amount of time. If we were a very precise operating system, we would sleep for that amount of time, okay? However, we know that we can't call use sleep and sleep for that amount of time precisely, because what it does is it always, if you were to not have this offset, what it does is it would always return you back. It would finish sleep at a time that is after your frame rate, right? So it just, like I said, it's a blunt object. It very bluntly is just like, you're we'll dump you out at a time that's like a few milliseconds after, what you wanted. And that's not good. That's not what we want. We want some degree of precision. We want to be able to hit that timing pretty darn closely every single time. So what I thought up, and what a few other people seem to have thought up, this is my little carafe of coffee while I'm on this particular topic. What we've thought up is, well, we acknowledge that this is not a real-time operating system, and that's fine. We're okay with that. So here's what we're going to do. We're going to subtract a little bit of an offset. We're going to subtract kind of a fudge factor here from this, so that we sleep a little bit less than so that when we wake up from this slumber, so when our thread wakes up, we're actually still just a little bit under our target frame rate, right? And then what we'll do after we wake up from this, so this is some variable time, right? And then what we'll do is we'll spin lock until we hit the timing, right? So we're acknowledging that this is kind of a blunt object. We have this offset. It's just this fudge factor of like 3 milliseconds, okay? And so whatever it is, it's going to be, you know, that amount of time minus these 3 milliseconds, right? And again, this number is, there isn't anything magical about this number. Like, this number isn't like some like law of the universe or anything like that. I kind of determined this number like empirically. So by that, what I mean is I played around with a bunch of different offsets just to see if I could hit my frame timing, right? Obviously, you don't want this number to be too big, because if that number is like 5 milliseconds, 6 milliseconds, 10 or whatever, then you're spinning longer than you need to, right? So when the system like wakes up, it's like, okay, now I've got to like spin some amount. Like, you don't want to spin that much, right? You want to spin the minimum amount of time possible. If you're gonna spin, you should spin the minimum spin, right? You shouldn't spin to win. Like, you should spin like some small amount, right? So spinning is basically losing. Like, spinning is not what you want. You're like literally losing. You're losing heat, you're losing power, you're losing, like, spinning is bad. But if you gotta spin because you're not a real-time operating system and you want to hit like a precise framing, then this is how you would spin, right? So this number I just kind of like determined empirically, right? So I was like, well, I tried 4, I tried 5, I tried 6, I tried 2. 2 wasn't quite enough. If I used 2, then I would sometimes, I wouldn't always, but I would sometimes wake up after my frame rate, right? Because remember, this is a blunt object. This U sleep. It doesn't really guarantee that you're going to hit any kind of timing, right? And so at 2, it was actually like not enough time, so that when I woke up, sometimes I would be after the frame time, all right? So then we have this while loop right here. This is the spin lock. So we are just spinning on this until the amount of time that has passed is greater than our target seconds per frame, you know, and that's kind of how we're doing that. So as soon as it's greater than target seconds per frame, we immediately dump out of this loop and we're at the end, okay? And this, again, is not perfect because it's not a real-time operating system. And so there's going to be, if we actually, so I think, you know, at this point we can probably run this and just see, you'll see what I mean. I'm going to run it. There is probably some bugs or probably some stuff that's wrong. Okay, what did I get wrong here? Okay, so target second per frame. That's second. Target seconds per frame. Target second per frame. Seconds per frame. Okay. So there's that. And then, okay, so 2 warnings. Gotcha. All right, so we were looking at this, right? And so now, you know, you see this output it's like all over the map. Well, let's run it and see if we clean that up a little bit. Okay. And take a look at that. So this is reasonable, right? You know, target frames per second, 29.999. That's like 3 figures. Sometimes it's not that. Sometimes it's a little bit different, so it could be less than that. You know, sometimes it's more than that. Like, you know, but this is way better. This is pretty darn well cleaned up. Again, not perfect, but I'm not really sure how much perfection we're going to be able to hit in a non-real-time operating system like this. And this is sort of something that kind of Casey and a lot of the people in the Handmade community, you know, talk about. I think it's actually like a worthwhile, you know, topic of our modern, you know, kind of our modern discussion is like, you know, the operating system really does kind of get in our way in a lot of ways. Like we want more control we would like more control because we could have better products. We could create better games. You know, imagine this is like in that 30 million line problem lecture. You know, imagine if there were a computer where your game, you know, ran its own operating system. And again, you know, maybe I'm wrong. You know, maybe there is some other magic that's going on under the hood in like some of Apple's like object-oriented CAV display link stuff. Maybe there's some magic going on under the hood that I don't know about. But honestly, you know, we'll see. I don't really think so. Like, I think that this is kind of about as good as we would hope to get in terms of hitting a frame rate. You know, we can actually flip that around. Again, I'm open to all kinds of discussion about whether this was right or not, because I don't like having to spin like this either. But it doesn't, you know, it honestly seems like, yeah. So another thing we can do is we can say milliseconds per frame, right? So it's just another, and also, like, you know, these are real 32s. These are floating point numbers, so they're not. You sort of run into like you know, floating point precision issues as well. So I get that. If we take the nanoseconds per frame and we multiply it by 1.0 e negative 6 instead, then that'll give us milliseconds per frame, and we can just do oops. So we can also do like you know, just to see. I actually like milliseconds per frame because I don't know, it's a more I don't know, the number is like, you know, I expect it to be like 33.3 or whatever. So something about that I think I like a little bit better. So we're gonna rebuild and then just and you'll see it's just like going to be 33.3, etc. Okay, so we're gonna run that. All right, and that's, you know, it's just another way of expressing the frame rate, right? So milliseconds per frame is 33.3, etc. Right? That's the number, and that's like pretty consistently 33.3. You know, yeah. So again, 3 significant digits in milliseconds seems pretty good. I suppose maybe, you know, it would, like, gradually over time, it could drift slowly away, and then like maybe after a very long period of time, there might be like one frame that tears or something. But then you know, or maybe not tears necessarily, because if we tell Metal, the GPU, to like only draw at v blank, right, when the monitor is not scanning. If we're telling it not to draw, then in that circumstance, it would maybe be like a missed frame every very occasionally, right? That's kind of how I'm thinking about it. Again, if somebody is more of an expert, I obviously invite your criticism. So that's kind of how I'm thinking about it. And it's probably so I could see how there could possibly be some like drift gradually, but then again, I get thinking, like, you know, this is not really like a real-time operating system. I doubt that many are, at least like these consumer grade operating systems. So, you know, it's here's what it's like. So, you know, some of you may know that I snowboard a lot, and I used to kind of compete in snowboarding, right? And one of the things that would happen is you go to these like snowboarding competitions, and like you'd show up, and, you know, to practice for a snowboarding competition, by the way, you're training during most of the winter season. You're hitting jumps, right? And you're practicing these tricks, like, and you're practicing your line of tricks, right? And on any given day, there's like rather variable weather conditions. So while I'm training, you know, maybe there's like really great sunlight, and I can see the jumps, and I can like plan my line of, like, you know, what I'm gonna hit and what tricks I'm gonna do, and the light is just very crisp and clear and direct, and I can see shadows, I can see shapes and plot my trajectory, right? And the snow is fast, right? On a nice sunny day, the snow is fast, and I can move, I can glide across it really nicely, right? And plan things out really well. But weather changes, and it's not always the same, and sometimes it snows and it messes up your jumps. And so it snows, and now there's like an inch of powder. And I like powder snow, don't get me wrong, like I love it. But now there's like an inch of powder, and instead of me being able to go into my jump, right, I've got I'm getting slowed down by the thing, and that now I can't get the same amount of speed. Or maybe the light is just like totally flat, and I can't, it's all just kind of like monochromatic, and I can't really like distinguish one feature from another. And so like I go up to the jump, but I can't really see where the lip of the jump is, and I don't know if I have my speed right, and I don't, I can't really hit my timing as well, and so that sort of throws me off. Or like maybe I'm just a little bit scared, or I'm like a little bit more timid now because I can't figure out what the timing is, and so like maybe I just don't look as confident as I would otherwise. Conditions, and when you're at a competition, it's like. Guess what? We're all competing, and they're not gonna like cancel the competition just because there's flat light and you can't see, or they're not gonna like sometimes they'll cancel it if there's just insane amounts of wind or snow or something, and like then we like just absolutely can't, like we know we can't do anything, right? Sometimes they'll cancel it for that, but most of the time like they're not gonna cancel it for like light or anything. And it's like everybody is all competing in the same field, right? Everyone that's there has to deal with that crappy light. And I sort of look at this, everyone that's making games sort of has to compete in this world where we got kind of imprecise timing, or non-real, like we can't control the operating system. That's like the weather, man. And so the weather just is going to be what it is, and we're going to try and hit this timing, but it's not going to be perfect, and we're going to kind of try and compensate for that. That's how I look at it. I think you kind of have to look at it for, if you can do the very best that is possible for you on this platform, then that's like saying I'm at the competition and I'm gonna hit the jump with, the light scares me. I don't know what I'm doing, but I'm gonna hit it. Like, and I could screw up, but at least I gave it my best, right? And so I kind of feel like a similar sort of thing applies here. Like, this could be wrong, but we're doing our best here. Given the circumstances, we're seeing what kind of timing we can get out of this like imprecise operating system. So I will leave you with that. And I'm actually going to Handmade Con tomorrow. I'm flying out, so maybe if you watch my videos, say hi. I'd like to meet all of you. So this will be interesting. I'm actually going alone. I don't know anybody, so it'll be pretty cool. If you like this, the source code will be available every day. Gosh, we're getting close to the end, like we really are. Just only have a few more things left and we'll be wrapped up with this. And then I'm gonna, let's see. Yeah, so obviously another kind of footnote, like support actual Handmade Hero before you ever consider supporting, my little side thing. And then, so I'm you can do that on Patreon, actually. You can support me on Patreon if you want to. I would appreciate it. Grab the source code. Do what you want. It's all free, man. It's open source. So enjoy, and I will see you next time.